Okay, for this video, for this session, we will continue to look at the third process or phenomena that lead to the failure of solid dielectric material. We call it as a thermal breakdown. Okay. Okay, for a material that have a certain conductivity, obviously there will be a Joule heating. Once we have a current conduction within the material, there will be heat losses to the environment, heat losses to the material, and that is known as Joule heating. Okay, due to current conduction. Okay, and this conductivity is increased as a function of temperature. Okay, once we have the as for the conservation of energy, we know that the current generated is equivalent to the the heat generated, the energy generated for a system is equivalent to the energy dissipated to the environment or to the material. Means this is known as conservation of energy. In this case, right, heat generated by a field, electric field, is equivalent to the heat absorbed within the material plus the heat losses to the environment. Okay, why the electric field generate the heat? Okay, how the electric field generate the heat? It's simply because with the high electric field region, that will promote for the higher conductivity of material. As simple as that. Alright. Once the conductivity increase due to the electric field, and then we will have the current conduction, and with the prolonged current conduction, it will promote or trigger for the heat generation, right? Heat generation. So to simplify this one, we can consider as heat generated by the field is equivalent heat absorbed by the material plus heat losses to the environment. Okay. Okay, heat absorbed is the heating rate that is used to raise the temperature. Okay, obviously once the material absorb the heat, then the temperature will increase, while the heat losses to the environment is while heat loss is considered that the heat or the rate of losses to the surrounding due to conduction, radiation, convection, and etc. to the environment, right? Okay, the rate. Once there is instability, okay, the condition become instability when, when the heat generated exceed the rate of cooling. Means that the rate of heat generated exceed the rate of cooling, then this condition will cause the thermal breakdown, right? Due to the imbalance to the energy balance between the heat generated and heat losses to the surrounding. Okay, what we call as thermal runaway. Okay, thermal runaway is particularly for insulation in power system that require the use of cooling. That's why we need the external cooling factor like oil, fan, heat exchanger, etc., and external cooling system, liquid, to maintain so that the temperature is acceptable temperature below the thermal runaway temperature. Okay, what is thermal runaway? Okay, we going to discuss about as we can see here, the electromechanical breakdown system are normally designed to run the temperature well below at which the thermal runaway can occur. Okay, what is thermal runaway? Okay, thermal runaway. Okay, thermal runaway is the temperature at which a small increment in temperature beyond this point, a small increment in term of the temperature will cause the failure of that particular material or distortion of the original characteristic of the material. That is means that the borderline between the before and the borderline between the a good insulator and the breakdown insulator. Okay, and okay, in this for certain cases, for example, within a short period of time, actually we in for the insulator to reach the reach the thermal runaway can happen under over voltage. For example, switching and lightning, that will take the insulator into the thermal runaway region. Okay, this is the region where the insulator or solid dielectric material can start to break down due to thermal. Thermal means heat, means that the material, the properties of the material become destroyed. That is the properties, and maybe we can't physically see. Look at the material, the melting. The material start to melting like a cable. The material start to show distortion in terms of the shapes and the size. That is what we call as thermal breakdown due to thermal runaway. This is the region, the border region, the borderline in, before the thermal breakdown occurred. Okay, thermal breakdown in cable design. Alright. As I mentioned, prolonged aging. Prolonged aging at elevated temperature means that the material is constantly at a higher temperature will lead to the chemical aging, and therefore the dielectric strength will be reduced, and then the insulation characteristic will be diminished. That's why we for engineering purpose we should design the cable or any power system appliances so that not to let the temperature get closer to the thermal runaway condition. How we can achieve this? For example, we have a power transformer, like I discussed in previous session. We have on-off, we have on-and, we have several type of cooling system so that we can avoid the temperature to get closer to the thermal runaway. Okay. Okay, thermal breakdown can be further explained related to dielectric loss, or we can say as tan delta. Okay, what is tan delta? Tan delta is the dissipation factor, or we can say as a dielectric loss. Okay, it's supposed to be okay, actually this topic will be discussed later under non-destructive test, maybe by Dr. Fairuz or Dr. Ree. And just overview for this one, current in normal case, okay, current through the capacitor does not lead the voltage across it. Okay, means that in this case it is 90 degree minus tan delta, so it's and then tan delta is considered as a loss angle. That's why we call it as dissipation factor or dielectric loss factor. Okay, in normal case, lossy capacitor can be represented by this circuit. We have the voltage drop across the capacitor, we have the voltage drop across the resistor, and this is the phasor diagram in which the tan delta lead and lag. In this case, is lag by 90 degree. Okay, it's okay, we can discuss later about this one. It's not it's just an introduction. And for thermal breakdown equations, okay, we have the equations here, which is W energy, AC due to electric field, current conduction, is equivalent to E, RMS value of electric fields, times F is frequency, times relative permittivity, times tan delta. Right? This is where what you need by the tan delta, the degree, divided by 1.8 times 10 to the power of 12. Alright, so we have this formula. Okay, and let's see just a simple calculation related to this formula, in which we have an observation from the single phase 25 kV per centimeter AC peak tracking test conducted at UTHM high voltage lab by Dr. Ree has found out that the silicon rubber material have a relative permittivity of 7.6, generate heat at 0.3 watt per centimeter cube. Okay, bear in mind with the energy. Okay, determine the dissipation factor angle, okay, or loss angle or delta in degree values. Okay, how we going to calculate this? We can simply just use this formula. Okay, tan delta. So by equation 1.7, we can actually just use this one, plug in the values. We need to obtain the delta. So we know the heat generated, we know the okay, we know the RMS value, the RMS values, we know the frequency, we know the relative permittivity, we plug in the value, will give you the result. Okay, and then question number 2, estimate the total heat absorbed in silicon rubber. Means that we know the conservation of energy is equal to heat absorbed plus heat loss. So what we want to calculate is actually heat absorbed by the material. So if the total loss in the surrounding during the test is actually 0.1 watt per centimeter cube. Again, a very simple math, but what most important for us to understand and how to use the formula. These are the solutions. The frequency is 50 Hz, obviously, Malaysia. And we have the electric field, single phase. It's mentioned here. Single phase. Okay, so we need to obtain the RMS values. Okay, how to calculate the RMS values is simply divided by square root of 2, and then that will give you the value of RMS value of the of the electric field, right? RMS value of the electric field, and then we have the relative permittivity. Heat generated is 0.3 and heat loss is 0.1. So we plug in the values, and then that will give you tan delta 4.5. Then at this point we need to convert into the degree. So just use the calculator, and then you can simply convert into 77.5 or 6, or we can mention it in radian, but the question asked here is in the degree, so the answer will be 77. And for the solution 1, for the heat absorbed, okay, we plug in the values, we obtain the values, and then in very simple math will give you, rearrange the formula, will give you 0.18. Okay, I don't need to explain in extra detail because it is quite straightforward. Alright, and then tutorial 2, I think this is almost the same. Single phase 4.5, tracking Manchester, high voltage lab. Again, they are the same. You can use the similar method by using different values here. That will give you what is required for this one. Okay, done about the thermal loss, thermal breakdown with some simple calculations, and now we come to the breakdown in solid. Okay, after prolonged operation, that is why we put as 10 to the power of 8. So it means that after a prolonged operation, after a certain period of time, maybe in years, after several years in service. And we will face the, okay, we have discussed about avalanche, electromechanical and thermal. Now we come to this treeing and tracking. This will take some time. Okay. Okay, in practice, certain breakdown that do not fall under intrinsic or thermal, but actually can occur after a prolonged period of operations, long period in service. We are talking about several years. Okay. For example, under the influence of environment, a conducting path may form on the surface of the insulator. We have the pollutions deposited on the insulators, and then from there that insulator, since the material are made of conductive material, metal and chemical, and then with the effect of the rain, and then that path may become conductive under humidity conditions, and then this one will trigger for the internal discharge, will surface discharge, and some of the internal discharge may also occur due to void. Okay, this is the condition in which the formation of a very tiny bubble within the material during the manufacturing process, in which the bubbles can occupied by the air or maybe by the water, because of the different relative permittivity, and with the high electric field, we can have the internal discharge. Okay, internal discharge, in which that will lead to the treeing process, growth or tracking and erosion. Okay. The formation of dry band. Okay, how the surface discharge occurred. Okay, we have the insulator. Say this is the surface of insulator, and we have the deposition of pollution layer over the surface of insulator, within the humidity, with the moist, with the maybe the drizzle from the rain. This one will become wet. Under fogging condition, this one will become wet, and with the electric field, high electric field, this will start to conduct current flow. This is what we call as leakage current. We will have the certain current conduction, and at the point in which the electric field is high, that one tend to evaporate. Okay, the water tend to be evaporated. Okay, once it's become evaporated, that one, okay, so we will have the interruption of the current flow. Once this one, we have the interruption of current flow, and then this current will start to bridge to come to this one. This is the thing, the phenomena in which we call it as a surface discharge activity. Okay, with time, if this discharge activity occurred on the surface of insulator, with time, with several years in service, definitely it will destroy the surface of insulator. Just like you burn your sandal, you burn your shoes, and it will become like make a carbonized defect on the surface of insulator. Okay, this is the example of the breakdown in solid. Okay, we have the treeing process. So this is discharge, and then this mark is due to the discharge activity, leave a permanent mark on the within the material. Okay, say this might be the cross section. It's happened within the material, and this is the cross section to show the effect of the treeing. Okay, the electric tree growth. Okay, how we describe the electric tree growth. Okay, basically we can simplify into this representation, in which the tree length, if we plot as a function of time, okay, tree length, okay, there'll be three obvious section in which we will have the interception stage, which is T1 at this point, and then we will have a propagation stage, and then we will have the runaway stage, and then we have a breakdown stage. Okay, we have 3 region. We can classify 3 region or 4 region if you want. The breakdown, including the breakdown. So and the okay, for the period, the time, the initiation of the 3 process will take a while for it to intercept, and then we'll start to have the string start to develop, the length start to become long, and then at some point it start to growth. With time it start to growth until a certain period of time. The process of the treeing will become conduct exponentially increase until it come to the breakdown. Okay, you can read this explanation. Okay, it can be classified in terms of these representations. Okay, stage of electric tree growth. Okay, we can classify. Okay, a tree may take some time to initiate. The interception T1 is dependent upon the field strength. Okay, E. Okay, the formation of the tree is depending on the electric field. So it can be mentioned as T1 is equivalent to 1 over electric field exponential. Electric field as a function to the power of alpha. In this case, alpha is a constant between 5 to 20. Okay. Okay, minimum field required is still uncertain. Once the tree has started, okay, these are the things that what I just explained before in this one. And then okay, once the tree has started to growth, it continue by electric discharge. Okay, and it start to branch out in maybe microns or less diameter. If the tree start to breach on the insulator, the electric breakdown will fail. Okay, and in this case, it does not necessary to occur immediately. It will take time, obviously, until it come to runaway stage, in which it will become very rapid. This is the threshold value before a total failure. This is what is called as a tree growth plot. Okay, and how we are going to relate between the length of the tree or the size of the tree with time. Okay, with time it will become it will eventually reach to the terminal runaway condition and lead to the total failure. Once it fail, definitely we need to replace with a new one. It will not replenish or regain its properties. Okay, parameter involving the electric tree. Okay, obviously material. What most important is the type of the material, the chemical properties, morphologies, and the electric field strength, the one that trigger for the treeing or discharge within the materials. The material itself, okay, the stretch voltage, and waveform. We also need to see whether it's DC or AC, as well as temperature. Say if the solid dielectric is installed outside, so the external factor like the heat from the sun will also promote for the formation of tree. These are 4 main important parameter that involve in determining of the tree growth. We may not see the tree growth normally is happen within the material, and sometimes it is also happen on the surface of the material. In case it's happen within the material, the only way we can see the treeing structure is by we try to slice it, and then we can only see from there. Okay, the 3 applications. the three growths are the key failure mechanism for high voltage equipment insulated with polymeric material. Okay, this is the three process is primarily important for polymeric type material. I mean the silicon rubber. This will not a normal case for the glass and porcelain. Normal case, but this is a constant problem to the polymeric material. Okay, or anything that polyethylene XLPE cable, and these are the things that we can see the close-up version. Water tree growth. Initially, it may start at a point and then it start to become bigger and bigger. Okay, as I mentioned, a polymer cable can be seen by slicing the material. Okay, slicing the material. Okay, you can read. This is what I just explained to you. Okay, the water tree itself does not lead to the failure. Okay, the formation of this one, it is well addressed as the premature degradations or degradation process of the solid, because the tree growth is not lead to the failure, but it will initiate for other mechanism to lead to the total failure. So we may consider this the tree growth as the premature degradations, or the process that lead to the deterioration of the insulator. Okay, these are again the example close-up version. We have, see, on the surface of maybe of the glass insulator, this one, tree growth path, and we have two, and at some point this one will merge and it will become bigger. Okay, and that's about the water treeing in XLPE cable. That is about water treeing in the solid dielectric. And now we come to the last one, which is electrical tracking. Okay, just like by its name, tracking means that a track that form on the surface of insulator, on the surface of dielectric material for after a certain period of time of operations. Means that, okay, just like a jungle trekking. Okay, if we talk about for those who like to climb a mountain, they would like to seek for the adventure of the jungle trekking. Okay, the trekking is developed once people has constantly use the route, and then it'll start to live a trekking on the within the jungle, just like this one. Okay, how it's happened? It's happened due to the electrical activity, including the discharge, including the corona, including the the surface arcing. This will somehow the formation of this one will trigger for the permanent marking on the surface. Okay, it will leave the marking and tracking on the same route, and once we have the current flow, once we have the deposition of pollution on the insulator, this pollution tend to deposit on this region, and then hence promote for the surface conduction, and that will lead to the dry band, and dry band will lead to the surface discharge activity. Okay, you can read the explanation here. Okay, these are the example. Okay, we have the post insulator. Okay, and it leaves a carbonized mark on the surface, like this one. It become erode. Tracking, this is tracking, and this is erosion. So tracking and erosion, see this one also, tracking and erosion is a complementary word. Normally it will come first tracking, then it will erode. It will start to deteriorate. Okay, tracking damage on outdoor insulator, as I explained before. These are the damage due to the insulator. Okay, like this one, say for example, if we have current conduction and it eventually can short or lead to the total failure of this insulator, in which it will punctured, it will become a hole here in this region. then will short circuit the high voltage electrode to the ground, and that is classified as total failure. Okay, this is again the explanation as I explained before. Over time, outdoor insulator will become covered with the pollutions, and then the leakage current start to flow, and then lead to dry band, and it will weaken the insulation surface, as I explained before. So we have this one. Okay, this is the dry band formation. We have the current conduction. Okay, this one. Okay, this is surface conduction. Once we have the dry band, that will trigger the arcing. The current will try to jump over this one to reach this condition that lead to this one of total flashover. Okay, this is the phenomena dry band. This is the physical what's happened on this one. This is considered intense. Why it intense? Because we are energized with the high voltage. Okay, we are energized with the high voltage. So we have several spots here, and eventually it will lead to the total flashover when arcing between the electrode here, the ground, and the energized terminal, or we can say energized terminal to the ground. It depends to what you connect the experiment. So this is what we call dry band arcing. The discharge activity that due to the dry band on the surface, a dry region on the surface of the insulator. Okay, prolonged spark. Okay, it's just what I explained. Will lead to the permanent conduction channel, and with the electric field, it will eventually lead to the breakdown. This is what we call total breakdown. Flashover over the insulator, and that will lead to the failure of the insulator. Okay, tracking and erosion. Inclined place. Okay, actually I just a quick one for this one is actually additional knowledge for you to read through. As mentioned, extra knowledge. Okay, Dr. Ree has conducted inclined plane experiment to study the tracking for his PhD. So you can see here, he provide the very detailed explanations how he set up the experiment. You can read by yourself the experimental setup, and this is the arrangement, and we have the silicon rubber here. Okay, this is sample before we start the experiment, and this is the result after we run the experiment. So we can see the tracking. Okay, and the material with the good one is like this. For example, it managed to resist the tracking. This is maybe that we can consider a poor formulations. This is the best formulation in which the physical damage is less. Okay, this is during the experiment. We have the arcing here, and we have the carbonized effect on the surface, and with the thermal camera we can see the capture the path of the current flow, and then you can read this one, the result, so that I don't need to explain all of this. You can read as a extra knowledge for you. Okay, so and what most important, this experiment is conducted with the standard British standard EN 60587. Okay, because we want to simulate for the tracking and erosion damage. Okay, that is just the extra knowledge. Okay, we can actually stop here if you want about the tracking and erosions. And then I think, and okay, that's about it about the failure in the dielectric, solid dielectric material, in which we have covered the intrinsic breakdown, electromechanical breakdown, thermal treeing, and tracking and erosion. I hope based on my explanation you can have a gist and have a good understanding to differentiate between these 5 phenomena And detailed explanation you can read in the lecture notes, and you can obtain in the Google or YouTube for more videos and work example. Alright, with that, thank you. Assalamualaikum warahmatullahi wabarakatuh.